ম্যাম আমরা লাইভে আছি।
Vincent, you can start now.
Good morning. I am Professor Vincent Shovi Gomes, and I have the privilege of being your host today. On behalf of Ashutosh College, it is my pleasure and honor to welcome you all to the second day of the International Webinar on Artificial Intelligence and Data Science, jointly organized by the Department of Software Development under BVOC Studies and IQAC. Before we start, I would briefly like to go through the theme and proceedings of the day one of this webinar. During yesterday's seminar, we learned 3 informative lectures from eminent professors. Professor Paramartha Dotto gave a lecture on the introduction to machine learning. Professor Sunil Karfarma discussed about the various issues related to big data analytics, and Professor Sripati Mukhopadhyay enlightened us on association rule mining. On the second day of the webinar, before the session, once again, we fondly remember our departed colleagues, Dr. Pooja Chatterjee and Dr. Nandan Ghosh. Now, we would like to welcome our 3 esteemed speakers, Dr. Amlan Chakrabarti, who will speak on deep network techniques for computer vision, Dr. Parish Chakrabarti, who will speak on designing and building artificial intelligence infrastructure, and Professor Shropto Shikosh, who will speak on cognitive routing for beyond 5G networks. Thank you so much, sir, for gracing our event today. So as you feel, it is quite an exciting itinerary that we have ahead, and I'm sure all the sessions will be enriching and informative for all of you. Now, I would like to call upon Professor Shantanu Modok to introduce our first speaker and our ex-student of this college, Dr. Amlan Chakrabarti.
Thank you, Professor Gomes. Good morning, ladies and gentlemen. It's a great pleasure for me to introduce our speaker, Dr. Amlan Chakrabarti. Dr. Chakrabarti is a professor and director of A.K. Choudhury School of Information Technology at the University of Calcutta. He also the former Dean, Faculty of Engineering and Technology of his university during 2016 to 19. He completed his MTech from University of Calcutta in 2001 and did PhD from the same university in association with ISI Kolkata in 2010. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA during 2011 to 12. He has almost 20 years of experience in engineering education and research. He received the DST Boy Scout Fellowship Award in Engineering Science 2011, Indian National Science Academy INSA Award 2014, JSPS Invitation Research Award in 2016, Erasmus Mundus Leaders Award in 2017, Hamiet Visiting Professorship from University of Cambridge, UK in 2018, Sikha Ratna Award by Department of Higher Education, Government of West Bengal in 2018, and IBM Quantum Researcher Access Award in 2021. He received multiple project grants in the area of embedded system design, VLSI design, quantum computing, computer vision, cyber security, IoT from different funding agencies like DST, METI, DRDO, DAE, Ministry of Social Empowerment, UGC, TCS, Intel India. He has also served in various capacities in various higher education organizations, both at national and international level. He has published around 160 plus research papers in referred journal and conference, 4 patents, 1 copyright, and have graduated 16 PhDs till the date. He is a senior member of IEEE Computer Society, distinguished speaker of ACM, vice chair of IEEE CEDA India chapter, and vice president of Data Science Society. Now I request Professor Chakrabarti to deliver his valuable speech to enrich us. Thank you, sir.
Yeah, thank you and good morning to all. And thanks, Professor Shantanu. Thanks, Professor Bidisha, for inviting me. Though it's a virtual session, but it's always good to connect with my college. So I was a graduate from this college during 93 to 96. I was a student of this college, and I'm very happy to be a part of this conference. It's what I will today. What I will try to speak as I find the topic in the topics which are already discussed by my friends and colleagues who have already presented and will be presenting. So it's basically machine learning, and all of us know that the deep learning is one of the very core area of machine learning now, and almost it is something that which is coming in a big way and already in a very big way. in many of the applications, be it image, video, text, audio. But due to a limitation of time, I'm not getting into the entire span of deep learning. What I will present today is basically a very important aspect of deep learning, which is its application in computer vision. And again, when we tell deep learning, there are multiple networks and multiple way we can apply those. My talk will be specifically on the very important concept of deep learning, which is the convolutional neural network, right? And I will try to explain that, and I will try to get into some basic concepts of convolutional neural network and how image and the deep networks can be well used for different types of algorithms for image processing. So let me start my presentation, and I hope that my slide is visible to all of you, right?
Yes, sir.
Yes, sir.
Okay. Okay. It's got freezed. Okay. So, yeah, it's a deep network techniques for computer vision is the title of my talk, and let's move on. So, this didn't happen. Okay. Yeah. So this is what is computer vision, right? And so computer vision is something that we try to imbibe, right? The vision means the capture of the environment through visual sensors, and then trying to get some useful insights, okay, from processing that data, right, and then take useful actions, right? And this happens in the biological world, okay, in a different way, right? It happens to the biological network, right? There are eyes which captures the environment, captures the scene in the environment, and then there is a central nervous system consisting of brain and nervous and your central nervous system, and that tries to process that information and tries to categorize the information. Here, this is a bird, or this is a house, this is a flower, right? And this type of recognition happens, and then we take certain decisions based on that. Now, the computer vision is just the mimic of that, but in the artificial domain, which means that we are using the computational techniques to do the same thing. So we will have a sensor, which will be an electronic sensor, which will again capture the environment in form of image and video, right? And we have to develop algorithms which can perform almost in the same way as the brain processing happens, right? So that the objects in the image are being recognized, right? Are being categorized, but by means of computational algorithms, right? And how it helps? It helps in many applications. It helps in applications such as there are a lot of autonomous environments are there now, right? We have the autonomous vehicles, right? In autonomous vehicles, we find that the car can detect the obstacles which are there on the road without a driver. Okay, they are all driverless cars. So how they do that? They do actually by the computer vision vision processes which happens there. There are sensors which captures the different obstacles in the road, right? It may be static, it may be moving obstacle, and then it tries to categorize that, hey, this is a man, hey, this is a rock, right? Or something like, hey, this is a traffic signal, so the car has to stop. Right. If we go to some simple other applications also, if we just consider the fingerprint scanning, which happens in the many of the organizations nowadays, right? It is also a sort of recognition, right? It is also a sort of biometric recognition of individuals, right? So there are many applications, okay, from robotics to autonomous operations through your searching on the web, right? When you search on the web, you have a lot of image and video video repositories, right? How they are searched, right? They are searched on basis on some information which is being tagged as a string, and then they are being connected with the objects. So this is what is computer vision, and this is a very interesting word. Yeah. So I didn't mention the other applications of the biomedical also, right? We have the applications such as there are software tools. In fact, we develop those tools in our research lab, okay, with collaboration with multiple hospitals. So those tools, what they do, they actually automatically diagnose the deformities in the organs. Once you give a CT or a digital X-ray or an MRI, right? My software will help the doctor to identify the patterns in those particular images, and that will help the doctor to understand those images better. Or in some cases, the software can go further, right? It can actually tell the doctor that, hey, this is a crack in the bone, this is the lumbar spine which got deformed, this is a nodule in the lung. So there are numerous applications which actually this artificial or computer vision techniques can help us in the present day. So now about deep learning, right? I'm trying to correlate both of them in my lecture. So this is a very fantastic paper for deep learning. I think all of you should go through this paper. This is a 2015 Nature paper, and the three persons, okay, Lee Kuhn, Bengio, and Hinton. These are the three persons who actually contributed a lot in the domain of deep learning. Actually, Hinton proposed the first the ImageNet winner. At Hinton's network was the winner of the ImageNet in 2012. Right, and on the extreme right, we have Andrew Ng. Right, I think all of us know him. Right, he's a phenomenal professor from Stanford, and he has actually pioneered deep learning, and he is okay. So this is a paper you should go through, and you should understand that what is the history of deep learning. Right, obviously Andrew Ng was not the author of the paper, but he's in the frame, because if I tell deep learning at the present era, these four pioneering persons will come up. Now, what is deep learning? As said in this particular paper in Nature, it is like that okay, it is actually computational models, right? Deep learning is computational models. They actually use multiple processing layers. Right? It is something like abstraction. So each processing layer try to generate certain abstractions which the next layer works, right? And we will know that how the abstractions are created by the deep networks in my lecture. But how it helps, right? It helps to understand the deep representations in the data. Okay, and those deep representations using multiple abstraction performs better in understanding the finer details of your image or video, right? And that's why deep learning has got a very phenomenal progress, right, in the domain of computer vision, right, or understanding the information, understanding the pattern which is there in the image or the video. And now, if you look into the history of deep learning, right, that means if we try to they all started from the neural networks, right? You cannot tell that, hey, deep learning just came like that. Deep learning came because it was already a process which was started from the neural nets in 1943, But obviously, we all know there was a stagnation period, right? Why? We will see that. So there was a good progress in the initial formulation of neural network with the Frank Rosenblatt's idea of perceptron, where he first proposed that here we can have a weighted combination of the input multiplied by the weights, and then we can actually generate a sort of linear partition, okay, by some sort of threshold function, by the threshold function partitions, and we can consider that hey, there is which gets above the threshold is class 1, and which goes below the threshold is class -1 or class 0. So he showed that this can be done, right? This was a single neuron. The perceptron is a single neuron model. Then it actually got extended. 1969, Minsky proposed that hey, we can have some sort of representation, but the representation is a linear representation, right? And the useful term here, you have to understand that when we try to solve a recognition problem, what it is actually, right? If we go to the first line in this particular slide, it tells that if you are trying to recognize something, right, you have to understand that how the information is represented. Okay, so representation learning is a process of recognition. So you have to know that what are the basic elements, what is representation, right? What is representation of a story, right? You have to know what are the basic para in the story. Then you get what are the sentences in the story, right? And then also you can look into certain words also in the sentences, and you can tell that hey, this particular text is a news about food price. Hey, this is a news about the sports. So once you go into the deeper and deeper representation, understanding representation, right, in the various levels, what you know, you actually try to recognize or try to abstract the particular content better and better, right? So that philosophy was being taught, but when it got stuck that the resources of a single neural network, was not sufficient. Then came in 1980s, late 1980s came the concept of multi-layer perceptron, which actually was magnificent. The multi-layer perceptron was the first push where it happened that hey, instead of inputs fitting into one neuron, can we have multiple layers, between the input and the output, right? And that was the multi-layer perceptron, which actually said that I'm trying to create different windows. So each of the layers are trying to generate different abstraction windows, right? And these abstraction windows builds up, slowly but steadily, and then comes to the decision. So let me give an example that how it works. Suppose I have a problem. The problem is something like I have to try to diagnose a person whether he or she is very ill person, or he or she is moderately ill, or he or she is fine. So how I do that? So what data I need? Suppose the data what I have some data of his or her blood test, right? So blood test data will give the condition of his or her cholesterol level, condition of his or her liver. There are blood tests which we can say about liver, the condition of his or her diabetic syndromes, or condition of his or her kidney function, right? First of all, I am not a doctor, and whatever I am telling is actually based on just examples, nothing related to the actual practice of medicine. Don't consider anything as something I'm telling medicine, right? So what I'm telling is just to give an example. So suppose I have a sequence of data of my blood parameters, right? So what I can do, I can try to take the weights of some data, like your blood sugar data or your HCN data, those are actually looking for blood sugar. So what I do, I actually abstract more weights to that data, right? And I try to form a node, form a node. Okay. If you look in my pointer, let me use the pointer. Okay. So trying to form a node. Okay, this node is trying to abstract the diabetic condition of the patient. So the parameters which are leading to diabetes, okay, will have more weights for this node, and the parameters which are not for diabetes, which will have less weights for the node. Similarly, suppose this node is for, okay, say for liver disease, right? Whether the person has a liver disease. So the blood parameters which are actually very well correlated to the liver disease will have more weights for this particular node, right? Others will have less weights for this particular node. So this way, say in this layer I build up two windows. Window one is for whether the person has a tendency of diabetic, or the person has a tendency of liver disease. Now I know a person is healthy when his liver, say I add one more node, right? I can add one more node for his kidney function, his or her kidney function. I can add one more node for his or her heart function. This way I can go on adding the nodes, right? And then what I say that, hey, the person is good when his or her liver condition, kidney condition, these conditions are within a particular level, and then then that may be this node, right? I take those weights and try to find out whether they are this is a good, and maybe these are extreme, right? And maybe I can put one particular node here to just to find that it's a mid level, right? We can have class 0, class 1, class 2, something like that. Now, can I go to another layer? Yeah, I can go to another layer. I can form one layer. Why? Because if the problem is changed, the problem is not focusing on the disease. The problem is that what will be the hospitalization cost of the person. So the hospitalization cost of the person again depends on the level of the disease, what he or she has acquired. So if I want to stop here, this is fine. But if I want to go further one layer, if I want to have that, okay, I want to also generate the hospitalization data, but whether this person will have a higher hospitalization cost or lower hospitalization cost, accordingly I will add one more layer. So this is the confusion I have seen in many of the students or early who try to understand neural network gets a little bit confused that hey, what are the roles of the layers and what are the roles of the nodes in each of the layers. This is the way you need to understand that each of the nodes in the layers are trying to extract a different type of permutations through the weights of the inputs and try to generate a different decision windows, right? And these decision windows are again aggregated to generate the final outcome, right? If you want to have a more extended outcome, which you cannot generate directly from here, then you have to go on adding layers, right? And this is the crux of what is a neural network, right? The limitation of time, I'm not getting into details of this, but why I try to say this is that you have to understand neural network well before you get into a deep network. Okay, so the multi-layer perceptrons. Now the big question is, hey, how I get these weights? Right? There are strategies like backpropagation, gradient descent, right, where we try to optimize the network in terms of the training data. So we have these are all supervised network. So supervised network means you have a training data, and the training data, that means you train the network using your data and try to find whether the outcome is as per the level given in the training data, right? If they are not, you have to again retune the network, right? And retune the network has some standard techniques, which I'm not covering in this particular lecture. Now from that onwards, from 1990s, it came that the people started to make the networks deeper and deeper, right? And the other type of networks, like I can actually, it's not only a feed forward, but I can also have a sort of state machine concept, right, where I can feed there is a sequence of states in the network, and each output propagates to the next input. Right, in this way we can draw. So these are the sequence machines which are called the LSTM. So all these started working in late 1980s, early 1990s, and that was That was the starting of deep learning. Okay. So what is then deep learning actually, right? So try to see what I have actually said, right? It is neural network, but what it tries to do, it tries to abstract the features in the multiple abstractions, and the abstraction grows actually from lower to higher, right? I will give an example soon on this. Okay, so if we look into the first, low level features, what does it mean? Like we all say low level features, but what it means? Low level features means which are the primary constituent features. So before you go to the edge, right? I think that I'm not getting into details of image and computer vision here due to the scope of the time, but I feel that you have the idea that what is an edge. So before I can detect edge, what I have to detect, I have to detect the derivative function, right? I have to evaluate the derivative value of the pixels in the neighborhood, right? And that derivative value, if it is higher than a threshold, I tell it's an edge, right? If it is lower than a threshold, I tell it's not an edge. So the low level features are something, the derivative values. So you see that some in the region the derivative values are quite high, and some regions the derivative values are quite low. So from the derivative values, I construct the edge, right? And that's one level of from the very primary level of feature, the derivative value, because you also require a kernel to extract the derivative value. So that particular kernel is actually extracting the first level feature, and then you go to the second level feature, which is the edge. Once you know the edge, you can understand that, hey, these are the textures of the object. Once you understand the textures of the object, you can now understand the boundary of the object, right? So it's also one thing works out here is that it also goes to a sort of spatial compression. When we look into the edge, we look into the nearby neighbor, right? We look at the nearest neighbor when we look into the edge. But when you look into the texture, we try to see a larger neighbor, right? A larger neighbor, which can be grouped. When we go to an object, we see a larger neighbor which can be further grouped. So it is something that you are using a microscope, right? And there are different particles in the microscope, different sizes of particles in the microscope, right? You are trying to detect everything. So what you try to do, you try to adjust your lens, lens the zoom or the focal length of your lens, right? And then you are trying to detect every particle one by one. So what you are trying to do, so the smaller particle, you will have the smaller particle which are at the base, you have a larger zoom, right? And then you try to find out whether the smaller particles are aggregated, and then you are trying to decrease the zoom one by one. So there is also a spatial compression which happens to detect the object, detect the features from the very final level to the higher level of abstractions, right? And from that we can. So this is what are the need of multiple layer. That's the need of the network in the deep network case. Okay. So from the neural network, right? If we try to get into the convolution neural network, which I am now here in this particular slide, there is a primary difference. The primary difference is the convolution neural network, unlike the neural network, which actually gives you input at a one shot. The convolution neural network works on patches. Why? Because the features are spatially correlated. So if you take all the pixels at one shot, right, you lose the spatial correlation, right? So what do? You try to divide the pixel. Okay, you try to divide the entire image into some patches, right? And your filter operates on these patches, right? And the filter moves across the image because it has to cover all the patches. So there are two terms when you try to tell a convolution neural network. One is the convolution and one is the network. What's the network? Because this is nothing but a neuron representation of your data. Okay, so you have the inputs coming to the neurons, right? And this is the weight. Okay, in the neural network we have a weight multiplied by the input coming to the neuron. right? In each neuron, you have a wet coming, right? A wet multiplied by input. So what you are having here is that this particular convolution filter, this is called a filter because it's extracting a particular feature. When you try to extract something from your data, we tell it's a filter, right? And this is a feature level filter, right? So this particular filter, okay, is represented by a matrix, two-dimensional matrix in a two-dimensional CNN operation. So you have a two-dimensional matrix which are represented by the weights, right? And these weights actually operate on the input data, which is your pixel, represented in a 2D spatial dimension. But you don't actually work on the pixel at a one shot. What do? You divide the particular divide the pixel information into patches, and on each of the patches, this particular filter, okay, or the weights of the filter work, right? And it moves over across all the patches. So one is the neural operation, and another one is the moving of the kernel across this particular information is something called as the convolution operation. Okay. So you see what happens here is that so you see this is the image, right? And the filters operates on patches on this particular image. Now from this one image, I have generated multiple outcomes of my convolution. Why? Because each of these defines a feature space, and each of the convolution outcome is for a one feature kernel. So what I have shown here is one feature kernel which is operating on patches on the entire image by sliding the operation. But there are several kernels like this. Why? Because you have to detect several types of orientations, right? You have to detect several types of patterns, right, from your image. So for each pattern, okay, you employ one particular filter. And so when you do the convolution, you have the feature space. Feature space consists of number of outcomes coming from each of the convolutions, and they generate the feature space like this, right? And then there is a step called ReLU, rectified linear unit. It is a normalization. It's just a normalization. What it does, it tries to neglect those values which so a filter can have high value and the filter can have low value. The filter high value means the feature exists very strongly. A filter generating a low value means the feature doesn't exist strongly. So if the feature doesn't exist strongly in a particular region, the outcome of the filter will be low. So there is no point in actually considering that at the next level of your abstraction. So this ReLU, what it does, it actually normalizes, okay, your outcome. So it makes, normally ReLU is a function which is something like max of 0 and z. Okay, max of 0 and z means if your value is positive, it retains the value. If its value is negative, it just pushes it to 0. So the ReLU pushes all the negative values to 0. The negative values which are not contributing, and it generates all the positive value and generates the next level of outcome from the convolution layer. Now comes the pooling. So what is the pooling? The pooling actually does a subsampling. See, the pooling actually compresses the spatial dimension of the information, right? And what it does, it actually takes a representative. It's a subsampling, means you have 4 pixels. Okay, 4:1 subsampling means 4 pixels are represented by 1 pixel. Okay, so you see what happens, that this particular ReLU layer, which are being subsampled with 4, right? From each of these 4 pixels, I take 1 pixel, and max pooling means I take the maximum value of the pixel. Okay, so the maximum pixel out of the 4 pixels will be there. So what it means, it is actually a sort of subsample which gives you which actually takes the lower level features. If this is the outcome of the first level of convolution, so it means that it has recognized the outcome, okay, and the spatial information of the image where the first level feature extraction have performed well, right? And this process goes on and on in multiple layers. right? And so you can from the derivative value you can get to the age, from the age you can get to the texture, from texture you can get to the object, and then you can go to the class of the object. This process goes on, and that's why the multiple layers are. Okay, so this is a work on convolution. As I say that this is the convolution process. As I told that it is convolution because the kernel trips over, okay, with a given stride length over the entire image data. But each time it only works on a patch of the image. It doesn't work on the entire image like a neural network where you have the entire input multiplied by weight supplied to the network at one shot. Okay, so this is what is there, and now we try to see what actually happens. Okay. So the patterns are much smaller than the whole image. That's why the consideration of patch. Okay, so the idea of patch can be clearly understood from here. Okay, so as the image is a larger dimension and the patterns are located in smaller regions, spatially smaller regions. So you have to, okay, that means you have to filter out on those regions. So your filter shouldn't be very large in spatial dimension. If it is very large in spatial dimension, it cannot resolve the patterns which are located in a smaller spatial dimension. So what do? You actually try to take, so this particular kernel operates on the entire image space, but it will identify the big only in this region. Because suppose this kernel was designed in such a way that the weights, if the shape of the pixel is something, if the pixel intensity variation is something like this, then only it will have a high threshold value. So in the entire image, it will only find this region has that particular. So now the filter generates a good high value in this region, which establishes the fact that this region is a big region. So in the highest level of abstraction, I can tell, oh, this particular object has a beak, right? And similarly, I can generate a filter for eye and can tell, oh, this object has an eye. Similarly, I can generate, okay, a filter for wing. I can tell, hey, this object has a wing, right? And then I can tell that, hey, this object has some legs or some paws. Hey, this object has a paw. So I can generate a filter for that. So then if I tell you, that means if I just tell any person that, hey, I have found an object which has a beak, which has a wing, which has an eye, and which has a leg, right? You will very easily tell that, oh, I'm talking about a bird, right? And this is the way the classification works. The task becomes very easy if I can extract the features in a proper way, right? And that's what is being done. Okay, so this is a big detector, right? Now the question is, okay, now you can ask me a question that, sir, how I will create this field? How I will create this particular big detector filter? You will create this big detector filter by a procedure which is really wonderful. The procedure is that you are training a network, which means that you have supplied to the network that, hey, this is a bird, bird image 1, this is a bird image 2, this is a bird image 3, this is a bird image 4, and you have to classify them as bird. So the filters, which may be of some other values, will slowly and steadily will adjust itself and will try to find that, here, what are the features which will lead to this particular identification of bird. And this procedure will lead, this is called a training procedure, and this procedure will lead to settle down all the filters, right? Suppose I give you some particles, right? And you have to generate different types of shapes to the particles. What do? So suppose you have to, okay, it's a container. You have to make containers of different sizes because you have different sizes of mangoes, say. Okay, right? You have different shapes and sizes of mangoes, and you create a container for each of them. What do? You will take mango 1 and you will try to fit that. Okay, what's the dimension of this, and we try to keep, hey, I got a dimension of mango 1, right? And then I take mango 2, which will be a different dimension, so expand the dimension. So So more and more mangoes I supply to you, right? More and more the dimensions of the mango, more and more dimensions of the mango will be known to you, right? And then if I give you any object, right, you will try to feel that, hey, whether it goes in this box or this box or this box or this box, right? If it goes to any one of the box, it's a mango. So this is the way how the training of the network, which actually adjusts the filters, right, and helps us to decide on the on those objects which are unknown after the training has been done. We can classify the objects, okay, after the training is properly done. Okay. So this is something, as I told, that you can have different types of filters. Like here, you can have an upper bit detector, you can have a middle bit detector. Okay, so this particular detector moves around. So the detector moves around. It doesn't. Okay, fine. Okay, it will work for both the images, right? It's a big detector. Whether the beak is here or beak is here, it is not important, right? You run the big detector on the entire image and you find, here there is a 1, there is a high value, so the beak is here. But again, for this image, you run the big detector on the entire image and you find that, hey, the beak is here. Okay, this is the way you can actually detect that beak irrespective of the spatial location of the particular filter, of the particular feature, because your kernel, your filter is moving around, and that's the advantage of convolution. Okay, so this is the concept, that the replicated feature, you are trying to find the features which are present in a multiple number of times in an image. So that's why you are moving the kernel, right? And that's the motivation of why the kernel is moved. Okay, move. This is a very fundamental question which the student asked, that, sir, why this this filter moves around? The filter moves around because you have to extract the features and their spatial information all around the image. So whenever the filter gets a high value, then the feature gets trapped, right? And you know that, hey, this is the feature I have received, that this is the spatial location of the feature. Okay. So this is the way you see what happens. So the big detector filter, big detector feature filter, convolution matrix, whatever you tell, will actually have a very high value in this particular region of the image, right? And it will record a high value. So now if I'm reading only this particular information, I can easily tell that, hey, this information means that there is a beak in this particular spatial region of the image, right? And that's a good information to classify this information, this particular image. Okay. So technically, there are multiple filters, as you see here. This can be filter 1, this can be filter 2, and there can be many more, right? And this filter actually, so how many distinct parameters you want to consider in each of the layers? See, that means these filters can be in any layer of the deep network, because as I told that a particular network consists of multiple convolution operations. So these are the multiple convolution filters, right? And how many filters you will choose is similar to that how many hidden node you will choose in a particular neural network. So how many parameters you are trying to choose in this particular network, based on that you take those many number of filters. Okay. So but the filter size depends on what is the spatial dimension of the feature. If I take a 3x3 filter, it means that the spatial dimension of my feature is 3x3, right? And it moves over and it tries to detect everything, right? So it's a sort of dot product. Okay, what it means, dot product? It's a simple weight multiplied by the input. So here the inputs are 1 0 0 0 1 0 0 0 1, and with each of the corresponding values of the weights. Okay, again I'm telling that if you can remember the neural network concept, these are the neuron inputs and these are the weights. So you multiply each of the weights with the corresponding neurons. Okay, the corresponding inputs, and you get the value. So that's the way, right? And you do a cumulative. Okay, it's a summation wi xi. So wi's are this, xi's are this, and you multiply wi into xi and you do a summation. So this ultimately generates 3, and this way, once the filter moves, right, you have the entire outcome which comes like this. So you see that you can easily tell that this filter was created like this because it will try to extract a pattern which is like this, all high in diagonal. And this has generated maximum in this particular, because this was the first operation, right? This was the first operation of the filter, right? And this first operation has an exact match. This is the pattern. So this first operation has resulted the value 3. Similarly, I have got a value 3 here in this operation. Why? Because the pattern in the filter and the pattern in the image exactly matched here also. So this is the way the filter works, and this is the way you can generate the patterns, and you can easily, that means the next level of understanding can easily work on this particular values that, hey, I have got a pattern, this pattern here, I got this pattern here, and I didn't find any patterns like this, okay, anywhere in the image. Right, and this way you can generate, okay, for different filters. Okay, so this is the pattern for another filter where all the verticals are 1. So you see this filter will generate a high, right, only here. It will generate a high value only here, right? So which is somewhere, I think, here, +1. Okay, so sorry, and this is the last one. So this is the last one, which is the 3 value. So you see that this particular filter, okay, has actually extracted this particular feature from the image, right? And it has scored a very high value here. So what you are doing, okay, that means you are generating the filter value, and you are trying to spatially localize the particular feature, right? And this helps for your next level of decision. So this convolution outcome is a sort of feature map. So what you get the values where are high and low, right? And you also get where the spatial location of the feature is. Okay. So now if you do it for RGB channel, okay, what I will do for a color image, yeah, you do it for color image, and for each color planes you have to do you have to operate the filters separately, right? And similarly, you will generate the convolution outcome also for each of the planes. It's called a plane. It's called the image plane. 3 image planes, or somewhere it is also said as 3 image channels. Okay, accordingly you get the outcome of the convolution kernel, right? And then what happens? Then you pass it to a fully connected network, which is a classifier. So now this part, okay, sorry. Yeah, so this part of the network is a normal neural network. Okay, it's a normal neural network. But what happened? What you have done here is that instead of giving the initial image information, which are your pixel information, what you are passing here is that you are passing here very high level abstracted features. So this x1, x2, x36, which goes into the last layer of the convolution network, which is a fully flattened network, instead of the data, you are passing the high level features. So the classifier work becomes very easy. So from data to the high level features, the work is done by the convolution. And from the high level features, so that the classifier can classify based on the high level feature, that is done by the fully connected network. So a deep neural network is just a combination of both feature extraction and classification. Unlike the traditional machine learning. In the traditional machine learning, you have to generate the features in one particular process. You have to do a feature extraction process, and then the feature extraction process, then the feature fits to the classifier, and then you try to generate a particular class boundary in the feature space. So the feature space construction and classification are 2 different jobs in a standard machine learning. Whereas in the deep network, the feature space generation by the convolution operation, and then it feeds it into the fully connected network, and then it actually does the classification job very easily, right? And that's the way it works. Now, this is the difference between a neural network. Okay, this is the difference between a neural network and a deep neural network and a convolution-based neural network. If it was a neural network, let's try to compare this. If it was a neural network, okay, this entire input set, that is a 36 input set, 6 cross image, the entire 36 input set would have connected to all the next nodes, because all the inputs should be connected, should be combined with the weight and should flow to the next level. But due to this spatial separation, spatial patches, what happens is that only some adjacent nodes are connected. So you see that, okay, for each of the operation, only some weights are required. Okay, so for this node, you need not to connect this node to every input. This output is only connected with a 3 cross 3 9 nodes, and this output is connected, okay, again with 9 nodes instead of entire 36 nodes. So there is a huge amount of reduction in the number of weights, which are the parameters of your model, right? And that helps in the training the network and make the network fast. And also this helps to spatially localize the feature. In the case of neural network, there is no way you can spatially localize the feature, right? So this reduces the number of weights as well as localizes the feature, and that helps in recognition problem. Okay, so fewer parameters and even fewer parameters, right? So that's the key of the convolution operation. So I'm not getting into details. This is already being done. I said the max pooling, right? So what it does, okay, the max pooling, it takes the maximum value out of this 2 cross 2 windows, right? And it subsamples the space, right? And it also okay, these are two things what max pooling does. One is that it subsamples the space and it tries to now look into the feature space which is over a larger spatial dimension. Try to understand this. In your primary feature space, your spatial dimension, okay, your spatial observation was limited. Now, as you are subsampling, right, what you're observing in this subsample domain is actually realistically it's a larger spatial dimension, right? So that is the one thing which is done by the max pooling. Another thing what max pooling does is that as I am taking the max value out of all the nodes in this particular window, right, it is immaterial whether 3 was here or 3 was here or 3 was here. So what it means that if there was a certain change in the big position in image 1 and image 2, right, that will not actually not actually generate a variation in the pulled output. So it tries to accommodate small variation, okay, small location. So it's invariant of small locational changes. So if the 3 would have been here or here or here, still the max pool value would have been 3. So this is the max pooling outcome where it takes the maximum value, okay, right? So that's the max pooled outcome. Okay, so it subsamples, it tries to, in each subsampling, it tries to work on a larger spatial dimension. That's why it subsamples, okay? So this I'm just skipping on. So this is this is convolution max pooling, and you try to push into the classifier, and the classifier works perfectly, right? Provided you have trained the network, okay, so that the filters are very perfect for the image domain you are using. So this is also a very valid question that, sir, I have built a network. Hey, I worked with dog and cats. Why it cannot classify trees and windows, trees and houses? The issue is that when you have trained your filters have tried to set their parameters so that they can extract the features which are there in dog and cat, right? And then they can
Tobik, start. I think the streaming problem has solved.
Hello?
You can start, Shobin.
Okay.
Sir, can you repeat the last slide once again? Because
okay, sure. I will do it. Okay. Okay. Yeah. The last slide means this one, right? This one or the previous one? Okay. So, is my slide visible to all of you? Is my slide visible to all of you?
Yes, sir, it's visible.
Yes, sir.
visible.
Okay, fine.
Yes, sir.
So this is where this is the snapshot of the convolution neural network, right? So this is a very well known network which can which can detect the handwritten text, handwritten numbers which are supplied as images, right? And to understand how this network, we can analyze the network, is that these values will be there whenever you see a network. You will try to get what are the values, and then you can understand what is the network. So suppose I try to give the example. This is a 28 cross 28 cross 1. It means that it is an image resolution of 28 cross 28, and the 1 means it is a grayscale image. If it would have been a RGB image, we could have been 3 channels. So it would have been 28 cross 28 cross 3. Now this image has been a little bit resized, so it made 24 cross 24, right? And this N1 are the number of convolution filters. So the convolution filters are, as I said, they are the parameters what you try to extract in the image. So they may be the tip of 2, they may be the tail of 2, they may be the overlap in the 2, they may be the neck of 2. So the different types of parameters you want to extract. Okay, so okay. Accordingly, you give the n1 number of convolution layers, and then I go with subsampling of this. So because it's a pooling. So subsampling here, 24 cross 24 reduced to 12 cross 12. So it means that subsampling is 2:1. So for each 2 pixel, that means I have taken 1 pixel, right? And it's a max pooling, right? And then I go on of this the same operation of convolution and right. And you see that as I move on in the upper layers, the dimension reduces. Why the dimension reduces? Because you are, as I told, you are trying to see the patterns over a much larger spatial spread, right? So at first you are trying to look into the patterns which are in the very lowest level, and then you are trying to look into the patterns which are in the next higher level in spatial dimension, and next higher level spatial dimension. And this way the pooling reduces the spatial dimension, and you can start the feature in a much higher spatial dimension. And that's the way you go. And then you have the flattened layer, and the flattened layer will actually have the sufficient high level feature space, which will be very easy now to classify whether it is a 2, whether it is any of the digits from 0 to 9, right? And that's the way any of the convolutional network works, right? You can have different type of architecture for different networks, but if you can understand what this network, what are these layers actually mean, right? You can code them and you can implement them. So this is where I end the CNN and deep neural network, right? And here I tell what are the activities we are doing at the School of Information Technology, A.K. Chaudhary School of Information Technology, University of Calcutta. We have a fantastic data science lab which performs ML and DL research. So we have groups who are working on computer vision, renewable energy, text analytics, IoT and edge analytics, cybersecurity, and quantum machine learning. So we have multiple funded projects, multiple collaborations with hospitals, with defense, with other institutions like IITs and ISI, CDAC, Samir, Sikkim Manipal University, and we have also funding and collaboration with industries like TCS and Intel, and very recently with IBM. So we are also this is one of the very upcoming work what we have started, which is called quantum machine learning, and we are the first group in India, who have contributed in a theoretical algorithm development, which is a quantum ant, right? Our is the first group in India who has contributed theoretically in the first ant colony version of the quantum. We have actually presented that, and that's why IBM has given us Access Award in this year, me and one of my PhD students, Mrityunjoy. So that's all. That the students, faculty members, researchers who are in this particular conference were interested with connecting us in the ML and DL research in the various domain. It will be wonderful, right? And please connect us if you have any interest in this domain. Okay. So thank you. So I end up here, and if there are any questions, I will be very happy to answer.
Thank you so much, sir. I'm sure we will learn and have a lot to take back from this lecture. Now I would like to invite Professor Rishi Bhattacharya for the question and answer session of this lecture. Rishi sir, please.
Thank you, Shobik, and thank you, Amlan sir, for your wonderful lecture. Coming directly to the question answer session, Krishnendu Dashgupta, a candidate, has a question for you. The question is, can we consider the neural network as an n-ray tree with each node having I childs having on the number of options available to it?
When you actually go to tree, it is something like a hierarchical, right, top to bottom, right? In fact, in a neural network, it is more squeezing from the bottom to top. Okay, so that's one of the fundamental differences, right? The weights, the weights can be considered as the way an ND tree can be derived, but you have to remember that here the nodes also contain the data, right? It is not that the weights are not, because normally the tree, in a particular tree, you don't actually move the data from node 1 to node 2. Here what you are doing, here actually you're moving the data. So node 1 data multiplied by the weight, right, is moved to the node in the next layer. So these are the certain differences in the computation of the data, compared to the standard tree type of storage, the neural network storage. Okay, so there are differences I have said, but obviously if you see some sort of hierarchical type of structure, you can have some correlation, but the operation, the computation part is very different in a neural network compared to a tree. Okay.
Thank you, sir. Thank you for your answer. Thank you very much.
Okay. Thank you so much, sir, for the valuable insights on the topic. Now I would like to call upon Professor Beauty Sarkar, who recently overcame COVID and is here amongst us and is still recovering from its after effects. We are happy to have you, ma'am. Kindly invite Dr. Parish Chakrabarti.
Am I audible, Toby?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Thank you, Professor Vincent, and good afternoon to all. But before introducing our respected speaker, I would like to thank our respected and lovable coordinator, Vidisha ma'am, who requested me last night and given me this opportunity. I know the reason, as she just wanted to encourage me and motivate me, as she always do this. Thank you, ma'am, and CSG ma'am, for your support. Now, without further delay, I would like to introduce our respected speaker, Dr. Parish Chakrabarti. He is currently working as a director, VPEEM consultant, LLP, and founder of B&P Robotronics Innovation Lab, and president of Rotary Club of Calcutta Innovation. He is also the life member of Computer Society of India, convener of Innovation Cell, the Science Association of Bengal, former mentor Innovation Hub, Birla Industrial and Technological Museum, Government of India, former District Coordinator for All India Council of Robotics and Automation, AICRA, Government of India, ex-faculty member, Techno India University and Institute of Computer Engineers. Today, he is going to talk about designing and building artificial infrastructure. So, without much delay, I welcome Dr. Parish Chakrabarti to deliver his valuable speech and enrich us. Thank you.
Thank you, ma'am. Ma'am, am I audible?
Yes, you are.
Yes.
Yeah. Thank you. Thanks a lot. Thank you for introducing me. First of all, I like to thank Department of Software Development, BVOC Studies, and IQAC Ashutosh College for organizing such an international seminar in such a difficult time, actually, and also for inviting me in this seminar. So I like to start my presentation. So I like to share my screen a bit. So I think is it visible? I mean, my presentation. I think.
Yes. Yes, it's feasible.
Okay. Thank you. Thanks a lot. So I'll start the discussion about designing and building an artificial intelligence infrastructure. So I like to start by saying that an artificial intelligence infrastructure requires a serious look at storage, networking, and AI data needs combined with deliberate and strategic planning. If an organization is going to implement an AI application, they has to look at certain aspects so that the artificial intelligence code they are trying to implement works perfectly well. So there are certain aspects that they have to look at. So they have to consider or enhance their internal architecture or features for running the AI applications or support the applications to work properly. These are few of areas that I will talk about that are very essential for an successful implementation of an AI system. So first of all, I like to talk about big data storage because data storage is an important aspect where artificial intelligence performance depends or work for. So for the big data analysis, not only the big data analysis, but the storage plans have to be taken care. So this is a very important infrastructure requirement for AI. So the biggest consideration is the data storage and specifically the ability to scale storage as the volume of data grows. What I'm trying to say is that there may be different needs for implementing an AI solution. So depending on the need, the data storage requirement also changes. Like let's say an example that an organization is working with uh, with high volume or high value neural network ecosystems where they are having many training data regularly coming into the system is analyzing the data and the AI is taking decision depending on that particular amount of data. So they for that particular kind of infrastructure or organization, they has to have traditional network attached storage that are ready or that are easy to scale with. As the amount of data comes in, the organization will have to have the data storage that can be expanded, and they have to consider the input output latency of the data. Now if an organization is say they are involved in real-time trading decision making, so for that kind of organization, input output operation per second is very essential. So let's take an example that an organization is working with say a trading decision making organization. They are working with say 2000 a number of stocks, and each stocks having about 5 days or 6 days or 10 days moving average. So depending on that data, the organization is taking decision, real-time decision of buying and selling, of acquiring the stocks. So for that particular organization, the data is fixed. Every day they are working with 2000 stocks data, 10 or 5 or 10 days moving average data of that particular stock. So the data amount is fixed, remain fixed every day. But for that particular organization, the input output operation per second is very important. They has to download the data from the server real time. They has to take the they have to implement that into their storage architecture, and the AI system will have to take care, or will have to work on that data. So for that particular kind of organization, input output operations are very important, and they have to implement all flash storage technology for them. So these kind of requirements will require, or this kind of requirement will be taken care when taking the necessary decisions. Also, the reliability to deal with the massive data amounts are required if the particular project is depending on some, or taking some decisions that are really important, like an autopilot system in a flight. They are taking a real-time decision, and the reliability of the decision and the data amount they are accessing is very important. Also for medical applications, medical AI systems, where the AI system is implemented in medical decision making, or say controlling the pressure on a oxygen storage system. So in that case, reliability of data must be important. For that, the storage has to be such that it can give the exact amount of data at exact amount of time. There should not be any delay. Maybe a microsecond delay can create a catastrophic effect. Also, to decide what kind of data storage an organization needs, they have to look into the nature of the data they are using. Like if an organization is implementing an AI system that is working with some sensor data, then it may be that the sensor data is getting stored and that will be analyzed later. So then a different kind of storage system will be implemented. But if the sensor data is being analyzed real time, then the data storage strategy will be completely different. So the nature of data storage is also to be kept in mind. And last but not the least, the data generated by the AI application. Each AI application, each AI implementation will generate a huge amount of data, depending on the algorithm they are using. So that data may need to be stored in a real-time system or in a flash system, so that data can be worked upon, and the AI system can easily handle that data. So these are the requirements, these are the points that have to look forward for an implementation and the storage. So there are these are some classification of data and different use cases. Like for distributed nodes, we can use Hadoop-like data structure, where the small distributed files are being utilized. To scale out network attached storage, or NASs may be required for large file processing systems. More traditional extracts, transforms, load implementations of big data. So NAS are very important for those kind of architectures. As I said, all solid state driven systems are for high performance in processing, where time is the essential thing, because the solid state device, we all know, are very good in providing data and accessing data. So those are very important. And for organizations that are working with experimental data, they are not decided, or they are not decided with what kind of data they are using. They maybe use object storage for a temporary period, because object storage uses flexible containers, and they store data in containers or blocks. And instead of RAID, they can allow object-based storage systems, and then they can finalize what kind of data storage they need to implement. So these are some considerations. Now, I would like to share a very good video created by Intel for AI data storage needs and applications. So I'd like to share this video with my audience.
AI solutions and Intel technology leadership provides an opportunity for businesses to access deep for insights and increase competitiveness by unlocking the potential of their data. The industry momentum shares growth powers that service AI, MLs, big data, and to continue. These shared priorities are hardened top line storage and capacity of storage. Access to more data is AI delivers new insights. C-score must support increasing efficient or accelerating access, moving data faster time and these challenges and addressing the need for scalability. Innovators are architecting shared data pipelines and leading storage technologies such as Intel Optane SSDs for performance and Intel SOCDN SSDs for capacity trading. Engines for unstructured and structured data is received from sources. Increasingly, more of this data is streamed in real time. Or intentionally, Optane SSDs is engines supporting high revenue. Even while these data capacity storage and keep critical sources online, less advanced data engines ULCDN SSD capacity storage. Data preparation steps include deduplication, transforming, and cleansing. Time spent in pipelines are 80% of the time. Optane SSDs as performance support high fixed workloads and only reduce coverage. Paired data brings culture to QLC and SSDs and store efficiently with scalability of all of their volume. Training is a compute intensive phase where training runs on data sets, storage, and limit the number of compute running on data analytics, which can reduce compute utilization and normal accuracy. Its intense needs, Optane SSDs can be used to improve compute utilization and increase data readiness. Less intense training needs can be read directly from QLC and SSDs, which deliver high updates. Automation, the training model is written to asset storage. Inference involves reading the training model of asset storage and applying that model data received from engines. Fast response are increasingly important as expectations for real-time results. Confirmed results are then written to asset storage. ULC and SSDs have equal performance with sequential data packs and current storage. Modern data storage efficiently manage increasingly intense requirements and provide scalability for future pipeline needs. Intel Optane SSDs performance to within as accelerate results and optimize working resources. Intel USC and SSDs and capacity tier provide latency and capacity scale. Wireless. To find out how Intel modernizes the AI storage pipeline.
So these are the different things that Intel is trying to implement for their pipelines. So next we are going to discuss about the networking infrastructure requirement for the AI systems. Infrastructure in networking infrastructure is one of the key components, because many of the organizations are implementing AI algorithms that depends on very directly on the networking requirement to provide efficiency at scale required to support AI and machine learning models. Organizations likely to need to upgrade their network. Like for deep learning algorithms are highly dependent on communications. So an enterprise network will need to keep stride with demand as AI efforts expand. That's why scalability must be a high priority, and that will require high bandwidth, low latency, and creative architectures. The companies also need to automate where it is possible. They should implement automated infrastructure management tools. Those are software defined networks are being combined with machine learning to create intent based networks. That the networks will anticipate demands and security threats and react in real time. So the network implementation is very important for each kind of AI implementation, and what the kind of implementation or structure they're using. So this is depending on that, the network infrastructure has to be created. For a successful implementation of an AI, it requires a machine learning use of algorithms to parse data and learn from that data being parsed, and then to make a determination or prediction, and without requiring some explicit instructions. So then only the AI implementation will be successful, which is the use of algorithm to parse data, the learning from the data, and making determination without explicit instructions or explicit coding depending on each and every stages. So this is a comparison, like in artificial intelligence, where we were using machine learning systems. So in machine learning, what we do is we supply past data, and using the algorithm of the machine learning, the network predictions comes. Now with the advancement of technology, we are now using the deep learning technology. So deep learning means the machine learning has recently evolved into more complex structured models, like deep learning, which uses neural networks for even greater insight and automation. Natural language processing, or NLP, is very important nowadays, because is another trend that's driven the recent AI advancement, and in the area of a virtual home or TI assistance. So NLP uses vocal and word-based algorithms and recognitions to make interfacing with machines easier via natural language cues and queries. So with deep learning, the structured data is also supplied with the past data or unstructured data, and the layer of thoughts are giving into implementation. All these layers are defined in the artificial intelligence infrastructure, and the self-driven network is the outcome of this implementation. So for each and every kind of the network requirement or the algorithm implementations, the network implementation is very much important, and it also depend on the maximum uptime it is giving. Actually, depending on the type of architecture or type of implementation, the uptime is also very required. And these are few strategic approaches that the AI machine learning competency is built upon. So this says that while creating the artificial intelligence infrastructure, they have to first decide the strategy to be implemented, and the particular data scientists will implement those strategies, pick the top priority projects, build the perfect data architecture. Who will build the data architecture? The data scientist, depending on your strategy, will build the data architecture and deploy the machine learning. So these are few very cliche terms, but very important strategies to have an artificial intelligence implemented. So after storage, then comes the network requirement. And now, depending on the type of network interface and the storage implemented, the artificial intelligence workloads have to be taken care by sufficient compute resources. So for AI implementation and for a successful implementation of an AI system, the particular sufficient compute resources are very, very important. We all know that today only the CPUs are not enough for implementing an AI architectures. The GPUs are very essential parts of an implementation of an AI infrastructure. GPUs have hundreds of simpler cores rather than having few cores in CPUs. Thousands of concurrent hardware threads can be run in a GPU, while single threading system were implemented in CPUs. GPUs can maximize floating point throughput. Very, very, very important, I'll say, for a successful implementation of AI system. We have seen lots of AI projects not being getting the proper output because of the throughput, the floating point throughput when not being handled properly. And the die surface for integers and FP units are very, very important. The most die surfaces are available in GPUs. So GPU is nowadays there are many type of GPUs available in the market, but for particular in artificial intelligence dependent GPUs are also there. So the much more cores, advanced workloads, parallel processing, high compute densities, image and graphics video processing, all are the positive sides of the GPU. And in the market, there are numerous companies creating AI-focused GPUs and CPUs, giving enterprise options when buying AI hardware. NVIDIA is all we know is a very leading in AI-focused GPUs. They have come with NVIDIA AI chips that are very, very popular nowadays and very, very efficient for implementing AI architectures. And very well known nowadays are Intel Narvana chips are actually created by in focusing the neural network processing systems, so very efficient for NLP processing languages. So in Narvana, almost all medical AI systems are using Narvana today because of because of their capability to handle neural network processing systems. And also there are many new companies coming up with very efficient chips, like one of them are graph core chips are very useful nowadays. Many small architectures, many embedded systems are using those graph core devices, graph core GPUs. Cerebras are very 1.2 trillion transistors are there, though it produces amount of heat, but liquid cooling is sufficient for cooling down these systems. So they are very efficient. So there are lots of choices available nowadays, so that and particular implementation of an AI hardware can be done. Now, we have talked about three very important aspects of network implementations and storage implementations, and then compute resources. Now, for AI implementation to be absolutely successful, the data that is being supplied to the AI system is also very important. So what we say is that the data that is being supplied to the AI system has to be a clean data. So what is meant by a clean data? So the clean data is what is not a bad data. So the bad data means the bad data can be inaccurate data. It does not represent the situation it is supposed to in an accurate manner. A data being supplied that is not in the it is not identifying the perfect situation for that it is to be utilized. The data may be incomplete. Some data are missing from the data sets, so we call them a bad data. So if you implement AI on that particular system, the AI implementation will not be there. The data, sometimes the data are inconsistent. They are not consistent for the structural format. So inconsistent data also give a very bad output for the AI implementation or AI algorithms. Invalid data is also a very or stops, maybe some runtime stops are seen because of the invalid data. Duplicates need to be removed so that the amount of data can be reduced, because huge amount of data is usually handled by AI system. But so the duplicate actually means an unnecessary use of expansion of your database. So duplicates need to be reduced. So these are the data we call bad data. If the data have these kind of features in them, we call them bad data. So what to do? We need to clean the data and make them turn. The data have to be cleaned and turned. Cleansing and turning are the two essential processes that turn the bad data into high quality data and increase the throughput and efficiency of the system. So fixing the errors, removing the duplicates, add the data necessary to complete the records. And data turning structure means the data to be consistent and usable regardless of the source. The data evolved as it cleans and turned in. So the process that is there to clean the data is such that when the data that has not been cleaned is called the raw data. So we start with the raw data in our hand, and then once the raw data is cleaned, it becomes a technical, we call it technically accurate data. This technically accurate data needs to be turned in an uniform data source. So these are the steps. So these are the things that make the data clean. And most large data cleansing projects are now performed with artificial intelligence, because it has been seen earlier that the data scientists are taking a huge amount of time to clean the data. So what is they're doing at it? The most of their time is getting wasted by cleansing this data. So nowadays, the artificial intelligence systems are also available that can be configured earlier, so that the data that is being supplied, that is raw data, can be handled properly by the AI system itself, and the data are made clean. That increases the productivity of the organization. The data scientist creates a learning model to predict matches. As more data enters the system, so it is like identifying the pattern. With pattern identification, the data, wrong data can be identified by looking at the different patterns of the data, and then the data is then cleaned, predicted, and matches with the system, and the machine fine tunes the model. So that is the architecture that is made to clean the data. This is first first in processing. They create the data more accurate and reduces the time spent by the data scientist by cleaning the data. So so we say that the life cycle for data processing is like that. The data is getting imported, then it is the margins of the data sets are then built. This is then rebuilt by missing data, by adjusting proper databases where the data are missing, the columns are missing, or they are losing some vital information in the data. So AI systems, AI algorithms can be made to do that. The data is then standardized and then normalized according to before putting into the database system. Finally, the duplicates are removed, verification and enrichment is done, and the data are exported. If needed, the cycle can be repeated also. So they are very popular softwares. One of the very popular software we use these days are Kenim, we say. Kenim is a data analytics platform, but that has a data cleansing module separately available. And this is an open source software. So the person who are working with the data analytics or studying data analytics can also use this software free of cost. So it is an open source software, very popular software. Data models are very easy to create. So there are structures that can be retained, and there are multiple type of graphs that can be created. So this is one of the very important software we use in data science these days, and it is also open source, so very easy to get. Now, the data we have talked about cleansing the data, using the data for the system. Now we are talking about the AI data management and governance. Deliver the data in a secure and efficient manner, and users who need it. So data governance means management strategies need to be ensured that users, machines, and people. So they are nowadays the users are not only people, machines are also users. So there may be a different kind of machines, different architecture, different devices connecting with the data system. The data is being used. The AI system are implementing in different nodes. So each and everything is now a user. So the user accessibility has to be particularly made for each and individual type of devices, and the data should be accessible from wide range of devices. Components need to look Companies need to look at technologies such as identifying and access management. Strong data encryption tools should form the part of data management and governance strategies. So data governance has three things. So technology, people, and process. These are three partners that get involved in the data governance, and they work upon the accessibility of data, the ownership, the accessibility, the security aspect of the data, the quality of the data being used, and the knowledge of the system, the knowledge of the system for the data, so the data can be used. So all these combines creates a data governance. Now, for making a system very important and efficient, artificial intelligence systems are now being utilized in IoTs, Internet of Things. So AIoTs, now the term is called AIoTs. The AIoT is crucial to gaining insights from all the information coming in from connected things. So connected devices uses AIoT. Variety of devices are there, products are there, sensors are there, so they are all connected with IoT systems. So the artificial intelligence system is accessing those data, creating data models, implementing algorithms, and coming out decisions. Assets, locations, vehicles, there are different kind of data may be associated with IoT related systems, and artificial intelligence systems for IoT has to take care of all these data available. And companies working in today's today's market need to take a very solid decision for implementing IoT systems for them, because by Strata, platform known as Strata, they have forecasted that there will be 10 billion connected IoT devices worldwide in 2021. So now we are using 10 billion connected devices. And by 2030, it will be about 25 billion devices. So this is a staggering improvement, a staggering increase of devices that is getting connected and giving data to our system. So companies need to focus on it. They need to create their network, data storage, data analytics, and security platform such a way that this staggering increase in devices, connected device and IO ecosystem can be included. And that includes data generated by their own devices as well as those of their supply chain partners. So everyone is collecting data from different parts, different segments, not only our own systems but our partners, supply chain systems. All of the connected parties in the organization are connected with IoT, so they are generating data, and the AI need to handle those data. So this is also a very important part of the infrastructure requirement for data. And finally, the training of the team is very important, because an successful implementation need a very successful skilled people for the artificial development. So usually talking about the infrastructure, we talk about the architecture, the storage, the network, the GPUs and CPUs, but I have included this particular one slide for team training also, because human resources are one of the most important resources for an successful project, any kind of project, not only for artificial intelligence, but they are very important. So They're data scientists, data analysts, developers, cybersecurity experts, network engineers, and IT professionals. They are also an infrastructure requirement, I should say, the infrastructure requirement for an artificial intelligence system, because without their knowledge, without their competency, we will unable to implement a successful system. So for now, I'll complete my discussion here. So that's it.
Thank you so much, sir, for your valuable information regarding designing and building artificial intelligence infrastructure. Now we would like to have Professor Rishi Bhattacharya to take the question answer session.
Thank you, Shobhik, and thank you, Dr. Chakrabarti. Actually, there is no such questions arrived yet. Once we get the questions, we will get back to you. Thank you.
Okay, definitely. Thank you. Thanks a lot. Thank you again for inviting me for such an organization. Thank you.
You are most welcome.
You're most welcome, sir.
Back to you, Shobhik.
Yes. Now I would like to call upon Professor Basudha Basu to introduce Professor Shropto Shikosh. Ma'am.
Thank you, Professor Vincent Shikosh. I have the privilege to introduce Professor Shropto Shikosh. Professor Shropto Shikosh is lecturer and research scholar at London South Bank University, School of Engineering, Department of Computer Science and Informatics. He has been a recipient of various national and international fellowships, including Gate, Erasmus Mundus, and Marie Curie. Currently, he is a part of EU Horizon 2020 project and has worked under Erasmus Plus and Innovate projects. His primary area of research is application of deep learning in networking and 5G communication systems. Now, Professor Shropto Shikosh will share his lecture on cognitive routing beyond 5G network. Welcome, sir.
Hello, everyone. Am I audible?
Sir, you're audible. Yes, sir.
All right, so let me quickly share my screen. Let me know if my screen is visible. Is my screen visible?
No, your screen is not visible. Can you try once more?
Yes, try once more. I believe now it should be.
Yes, it's presenting.
All right.
Yes, sir.
All right, everyone. Good afternoon. Good morning for me because it's not 12 yet. This presentation, before I start, I'd like to thank the organizers, first of all, for inviting me and for asking me to give this presentation. That's the first thing. Secondly, I was watching the previous speakers, and I'm really glad that the way these presentations are ordered, because the first presentation was based on the nuances and the theories behind machine learning and deep learning. The next one talked about things like IBM and AIoT, which is the application of machine learning and deep learning on networking. And now my stage is set up, so I can talk about some applications or some practical applications of machine learning in a specific problem in networking, which is called routing. So I believe the listeners are a bit familiar with the concept of routing. So, however, I'll be make this discussion very much basic, so that anyone who is not familiar with the basic concepts can also grasp. All right. The topic is cognitive routing for beyond 5G networks. Initially, if you see the term beyond 5G, it might seem like a marketing gimmick, but it's not, trust me. The reason we don't call it 6G or something else is because 5G is still rolling out. And here in Europe, we have a couple of vendors who have started rolling out 5G. In India, we have started testing 5G infrastructures, but we can't say that we have done the full rollout first. Secondly, the full-fledged implementation of 5G. I will talk about the the promises that were brought when 5G was first put in the table. But some of the topics which are still under research, and therefore we call the remaining topic and some advanced topics, including the beyond 5G network. So this could be called 6G, this could be called 5.5G, we don't know yet. But these are the topics which are not covered in the present deployment of 5G. Now, any network needs a routing feature, and routing essentially means that when you, let's say, transfer some data from like point A to point B, we need to find the best path, right? So, for example, you use Google Map when you are trying to, let's say, travel in an unknown city, maybe. So you need to find the optimal path. The same way, packets or data, when they travel across the network, they also use a technical routing that does this. Cognitive routing is a special type of routing algorithms, a class of routing algorithms which uses the machine learning and deep learning features in them. So we'll talk about it. We'll see what are the demerits of the existing routing models and what these machine learning and deep learning models can add on top of them. So I'll first start with a concept called self-organized network and knowledge-defined network. Now, these are the very essential terms to understand the rest of the lecture. Although they are not new terms, but they are kind of inherited from the previous generation of mobile communication. And once we understand this, then we'll see what is called software-defined routing. So what is software-definedness, if I put in that way? What is the feature of software-defined networks? We'll see that. And then a model that we have developed in our university called SOCDN or SOCDN. It's not a standard term yet. We are working on this term to patent at the moment. So this is a new type of network that we have produced in our laboratories with collaboration with other laboratories as well. We'll talk about that. So this will create, this SOCDN will create a kind of platform on top of which we will run this cognitive routing algorithms. All right. For those who are a bit interested in the nuances and the inner working of these algorithms, I will talk about a bit of the mathematical modeling. So in case if you're a researcher or you're a master's student, want to do research on routing, this could give you some ideas. And finally, some test results, some demos if possible. And mostly I would be expecting questions, because this is a very new topic, first of all, and these are topics which are not normally covered in the university lectures. So I will try my best to make it as lucid as possible so that everyone can get it and ask me question if you have, right? So let's start with the discussions. So I put this figure. Oh, by the way, there are figures which are not made by me in the presentation. I will talk about those, the sources of the figure. This one is not. This one is drawn by me. All right. So there's no copyright claims on this. All right. So this figure actually summarizes the 5 generations of industrial revolution. Now, the reason I put this figure is to give you a platform or a basis that why would we need this self-organized network? What is the necessity? What are the challenges that this particular network would solve, right? So if I see the whole history of industrial revolution, we can see it started at 1700 in Britain, and the primary objective was to mechanize production, right? So mechanization was the first iteration of industrial revolution. Then in the second iteration, electricity came, and the mechanized device, which used to be like steam powered device, now are electrified. So electrification was the next stage. Then the transistors were invented, and digital logic was formed. If you're familiar with Shannon took the Boolean algebra and made into switching algebra, and then we started creating all the Boolean logics into logic circuits. And from there, we started digitizing analog signals. So digitization was a third iteration. Then we went to something called globalization. So globalization is a bit of vague word, but the actual job it does is to integrate different types of industries together, right? So, for example, you have a car which is essentially a heat engine, which basically creates mechanized energy, and you can use electricity on top of this, and or programming on top of this to make it more efficient, right? So, globalization essentially means that using different features, a different type of engineering features, and you can blend them together. Now we are moving towards automation. 2020 is the age of automation, and it will go for, if not half a century, but at least 20 years from now, right? So we have seen that how things are being automated. We have seen things like IoT gateways, like Alexa, right? We can just speak with that device, and that can control your entire room, lights and fans, all these things, right? So now we're moving towards automation. Now this is a kind of a summary of the timeline, but at the same time, if we see two more things, one is to empower this iterations of industrial revolution. Two technologies played significant role. The first one I would say is the telecommunication technology. I'm sorry, if I can just pick a pen here. Don't think this is working. All right. Anyways, so the first one, the telecommunication technology that gave the communication platforms. When devices are communicating with other devices, you need a network in between them. And there was a series of development that have been there for this long. The other technology was machine learning. Now, initially, if you see their origin and the development structures, they used to be two different timelines. So the first network, for example, the public switch telephone network, we're all familiar with. We had these telephones at our home, which are connected via RJ11 connector that carries the two copper wires, and they are connected to the switches which are placed in the telephone exchanges, and then those telephone exchanges has the connections between other telephone exchanges. That used to be the earliest form of networking, right? PSTN, public switch telephone network. Then after, people realize that, all right, human voice is only 20 hertz, 20 kilohertz at most, but these coppers can carry up to megahertz or gigahertz of frequency. So why don't we use those frequencies to carry something else? And therefore, data network was formed. Okay, so those residue frequency bands now started carrying data, and DSL, digital subscriber line, were invented. We moved from circuit switching to packet switching. X.25 were invented. Then security aspect came in. For example, people started using same network, but they don't want to share data with others. So then technologies like frame relay, MPLS, VPN, these technologies came in. Now, after that, if we see the state of the art, we are moving towards a generation called the software-defined WAN, software-defined wide area network. What does it mean? It means you have a network, it's typical WAN network, but these are software defined. Although I haven't described what is software defined, software definition of a network, we will come to that point. But at the moment, just try to track this timeline. So at the moment, we are in the age where software defined WANs are standard, right? All the major ISPs are now moving to SD-WAN deployment. Now, if you see the other timeline, the machine learning timeline. So perceptron was initially born. Then we had we call the winter age of machine learning and deep learning, because this ZOR problem was could not be solved at the time. After the 1990s, backpropagation was invented. Deep learning was born. And then we had a problem that, all right, we have algorithms, but these algorithms are extremely recursive in nature, right? So if you're coming from a programming background, you know what I mean by this term. So how to solve it? And then somebody realized, all right, we have these GPUs. My previous speaker already mentioned about it. We have GPUs which are designed to do floating point arithmetic and parallel computation, and especially linear algebraic computation. So why don't we use deep learning computation with GPUs, right? And this is what we call the general purpose GPU computing, or GPU computing. And now if you ask at the state of the art of machine learning, I would say if somebody wants to create a machine learning program, he might not ever attend any class of mathematics, any class of machine learning, but still with 3 or 4 lines of code or even drag drop, he can create a machine learning program, right? Because of this deep learning APIs, application programming interface. Now, these APIs are coming from different programming language libraries, and the main objective of this API is to abstract the inner working of these machine learning models. So now we're in a stage that a network engineer, without having any knowledge of machine learning, can leverage those machine learning API and start using it on their networking problem. At the same time, the software-defined networking has become more software-defined, if I put it that way. That means a software engineer or a machine learning engineer doesn't need to know the inner working of network devices, right? So now we are coming to a convergence where these two technologies are coming to a single point. And this is what we call a self-organized, knowledge-defined networking, okay? I'll break down this term into pieces in next slide to get more out of it. Now, if we ask about the need, because if there's no need, there's no point of doing research, always remember the need comes from industry. So industry faces a problem, client wants something, and the industry wants that problem to be solved. That produces the need. And that need then gets translated into a mathematical or a scientific problem, and then researcher gets their job to solve that problem, right? So from the industry's point of view, we are now looking at features like this, like autonomous vehicle, right? We are kind of automating, mechanized devices, intelligent control systems, high reliability, zero-touch provisioning. This is an important stuff. Zero-touch provisioning, or ZTP, something called ZTP, means you bring a new hardware, you just connect to a network. That's it. The network has a responsibility of understanding what hardware it is, what kind of configuration this hardware wants, and based on that, it will remotely configure the router. So you don't touch that router. You simply plug the router, and that's it. And finally, another technology called virtualization and softwareization, which is also there. They are basically enabling this cloud technology. All right, so that's the summary of this kind of centuries of industrial revolution. So I think I have set up the stage, the need of the blend of software-defined networking and machine learning. All right, let me move on to the next slide. So this figure is not mine. This is a very common figure. Any 5G book or any student works in 5G knows this figure. It's called IMT 2020. Now, this figure is basically a standard that says what are the promises that 5G made when it was first put into a table. There are 3 features that was actually coined. The first one is called the enhanced mobile broadband, or EMBB. That means a lot of speed. Now, as a layman's perspective, if you ask somebody that what's the difference between 3G and 4G, 4G and 5G, you see the immediate answer would be 4G gives better speed than 3G. So I'm expecting 5G would give me better speed than 4G. It's not completely wrong. It is one of the feature of these generations. So speed is one of the throughput, technically, if we say in that way, is one of the other feature. But always remember, this throughput is basically a byproduct of something, right? So something happens inside the architecture, therefore we get a high throughput. So enhanced mobile broadband is one of that. So it gives you a lot of bandwidth. So you can now think of streaming a 4K video while commuting in a train, maybe. So for a lot of us, it can be a trivial issue, but from a networking point of view, it's a huge problem, because when you are commuting in a train, you are changing the cells, and every time you do a change, there's a handover happening. A lot of registers gets assigned, and new computations are made. But still, the time that it takes should not drop a single frame when you are streaming a video. That's the beauty. All right, this is enhanced mobile broadband thing. Another thing is called massive machine type communication, MMTC. This is mainly IoT. Okay, so now we are talking about humans are not communicating with computers. Computers are communicating with other computers. I give you an example of it. So think of a microwave oven that has a smart chip inside, and it also has a Wi-Fi radio. And when you buy this microwave oven, you paired it with a Wi-Fi, and then anytime this microwave faces any difficulties, any circuit stops working, it should identify that and create kind of a self-diagnostic report using the Wi-Fi sends to the company, the manufacturer, and the manufacturer side, that is another program that would interpret that report and create a call to a specific person who is specialized on solving that problem. So even if you are not familiar with it, that's fine, but this is going to come in next 5 to 10 years. So in abstraction, these devices are communicating with each other, and you are getting a call from the company that, hey, I got a self-diagnostic report from a microwave, and this particular part is faulty, so I will come on that day and I will replace that. So this is what a real life example of MMTC. The last one, URLLC, is a mouthful, ultra reliable low latency communication. This is the part that 5G could not achieve. Okay, this is something that was promised, but unfortunately it wasn't achieved in a way that it was proposed, right? So what is URLLC? I don't want to get into technical terms here. A lot of technical jargon would come in that case. Let me give an example also to understand this. URLLC would empower or leverage a technology called tactile internet. Tactile internet means, think of a surgeon is doing a surgery in United States. The surgery is actually taking place in India by a robot. Now the problem here is, let's say the surgeon is holding a scalpel, and the scalpel has something called a haptic feedback actuator. What it does, it basically vibrates in a way that you feel that it is kind of giving you a feedback. Okay, so I'm not gonna put any promotion here, but anyone who has used iPhone 7 or iPhone 8 knows that the actual tap button there, the circular one, is not a button. It's basically a glass panel, but the way it vibrates, it gives you a sensation that you are tapping it. That is called a haptic feedback actuator. So let's say that's the actuator which is placed in the scalpel. Now, this surgeon is wearing a VR headset, for example, and he is getting an illusion that he is doing the operation. But that tap this surgeon is making on the scalpel must be coming across this entire network throughout the internet to that robot which is doing the actual surgery. The moment this scalpel touches the actual person, the tissues of that person will give a resistance to that scalpel, right? Now this resistance must be sent back to the doctor who is doing this surgery virtually. Now think of a scenario, what if there's a lag? The surgeon puts a tap, he didn't get the feedback, so he might think that I didn't tap properly, so he put more pressure. But the actual reason was there was a delay in the network. Therefore, this tapping actually occurred twice in the actual surgery, and you can understand what catastrophe may take place if that happens. So we must somehow ensure that the network in between this doctor and the robot is ultra reliable, and there is no latency. So the latency is there. Of course, there must be some latency, but the latency is so small that the human sensory organs cannot sense it. All right. This is where we are now moving towards beyond 5G. We are now talking technologies which would, leverage some other features that would, result this this feature called URLLC. So let's see. So a proposed networking model that is presumed to be providing this URLLC is called self-organized network. Now, self-organization is not a new term. It was first coined during 3G time, and then 4G also inherited it, add some new feature. This is what we can see the 5G and beyond 5G's version of self-organized network. So you normally call it SON, S-O-N. Now, if you see SON and you dissect it, you get 4 different dimensions of it. The first one is called self-optimization. So what self-optimization does, so those who have done some course in optimization theory, operation research must know any optimization problem basically has an objective function that we want to minimize or maximize given a set of constraints. Okay, these constraints are called policies. My previous speaker here, termed this IBN, right? So intent-based networking. And if you simply Google Cisco IBN, you would see the steps are you write a policy first, and then based on the policy, the network will react, right? So this policy is basically, mathematically speaking, is a set of constraints. Now, self-optimization is a feature where the network knows when to call this optimization function, right? So it basically monitors the network continuously. It sees the network's behavior and it knows when to call this optimization function, the self-optimization. Now, when you have to optimize a function, you end up having an optimal set of values of the free variables. And then what? What do you do with those free variables? You go and configure your underlying devices with those free variables. It's basically a sound engineer is listening to a singer performing, and he's tuning those knobs so that the sound output is optimal, right? So those tuning are basically the configuration part. Self-configuration says that we don't need a human to do that. The machine or the network would be so much intelligent that after it optimizes the objective function, it will get those free variables, optimal free variables, and will configure the devices automatically. Self-healing means, what if my primary device goes down? I should have a backup device, right? I should be switching over to that backup device seamlessly. Now, in networking, there's a whole class of protocol that exist and serve this purpose. They are called the FHRP family, or first hop redundancy protocol family, and they're like mini protocol falls into that standard that actually does the same job. So if you have lost your primary gateway, you are moving to a secondary gateway. Now, these 3 features, self-optimization, self-configuration, and self-healing, are the features of SON in 5G. The 4th feature, self-learning, is what we call the beyond 5G feature. So now the network is not only self-aware of itself, it not only can optimize, configure, and heal itself, but also it can learn from its past. Means the way this network behaved previously, based on that, it learns from its mistakes, and it basically creates a learning model in a way that it would try to prevent that to happen in the future. This particular problem in machine learning is called a recommendation system, or this system is called a recommendation system, and the problem is called a deep reinforcement learning problem. Reinforcement learning problem means anytime you make an action, you will get a reward or a penalty based on your action's consequences. And then based on your reward or penalty, you recalculate or rethink that, did I take a right decision, right? So this is called a deep reinforcement learning model, and the resultant system is called a recommendation system. Now, when you combine these 4 features, we get something called beyond 5G SON. Okay, so in this particular lecture, I'm going to talk about routing as a self-optimization problem, network automation as self-configuration problem, high availability for self-healing, and network intelligence for self-learning. Now, because of the limitation of time, I would only talk about self-optimization. Okay, I will touch upon the other three, but I will mainly talk about the self-optimization, which is routing in this case. Now, what is software-defined networking? Well, software-defined network, I remind that one of the story that when I was doing my master's, SDN was a very new topic, and I to be honest, I took a huge risk by taking this subject as one of my master's thesis, that SDN, and we didn't have enough information at that time. But one thing I understood, that SDN is basically doing something what's called segregation of control plane and data plane. Okay, now control plane and data plane, they're fancy word. Actually, they mean that control plane means the part of the circuits of a network device that produces packets or consumes packets. Okay, the data plane means the packet arrives on this plane and gets forwarded. If they're not consumed, they're not generated. That's it. Okay, so let's say I'm sending, I'm making a call, for example, from UK to back home in India. So this call is sending a series of packets across these 5,000 miles of networks, and there are devices in the middle which are receiving it, processing it, and forwarding it. They're not consuming it. The device which is consuming and producing the packet is the nearest cellular tower which is connected to my phone. Okay. Now, why do we do that? Why do we segregate it? This answer, I would say, is not that simple to give in this webinar, but intuitively you can understand that all the existing networking algorithms that we study, they are distributed in nature. And the problem of distributed algorithms are, we must have a communication mechanism. So when something happens in one machine, this algorithm needs to update the other neighbors about that change. And since the processor speed is far higher than the bandwidth of a network channel, you have a bottleneck. You spend a lot of time in just communicating with other devices than actually processing it. Okay, so when you segregate it, you put all the brains of all the network devices into a centralized location, which is called a centralized controller, and you left all your underlying devices dumb. Okay. The next property is programmable. This is easy because if you want to program a device, you want to override its default behavior, you can do that with SDN. Open standard and vendor neutral, because the first standard that was coined on SDN from Stanford, it was OpenFlow, and it is basically an open source protocol. Now, I highlighted one feature which is called native support for policy-based routing. Now, this is very important. I don't know how many of you are familiar with this term. Let me give you a quick example of PBR. Normally, routing works in a way that a packet appears on a router, and the packet has a layer 3 header which has a lot of information, but 3 or 4 are the most important. The source IP address, where it's coming from, destination IP address, where it's going to, TTL, that how many hops you can forward this packet from this point, and MTU, that is maximum transfer unit, that how much data you can send or receive as a single go. Now, the way that typical routing works, you see the destination address and you query on a data structure called a routing table, and you ask that, hey, do you know what is the optimal exit interface for this network? And the router says either an interface or it says, I don't know. If it says, I don't know, you drop the packet. If it says there is an interface, you simply forward the packet. That's it. So this is called destination-based routing. So you send the packet based on the destination. But in a complex networking scenario, this is not enough. There would be scenarios where you need to tell the router that to follow your rules, okay? Override the default rule. And this is called a policy-based routing. And remember the policy I mentioned as a list of constraints. So you put those list of constraints, and based on that, routing will take place. One example is firewall. So you may block somebody from getting into your network. So when a packet arrives, instead of seeing the destination IP address, it will see the source IP address. And if the source IP address belongs to a specific class, it will drop it. Do you see how it is different? Now, why natively SDN support PBR? Because the way PBR works in normal router is as simple as a if-then condition. Okay, we call we put a fancy name like a route map, but it's basically a if-else condition. If the condition is satisfied, then you take this action. That's it. And it's exactly what OpenFlow does with something called OpenFlow table. You put a match statement that matches a condition. You put an instruction. If the match takes place, then you follow the instruction. And if you have multiple matches, you have a tie, you break the tie with a priority. That's it. So with that, SDN became one of the, the choice of network engineers and network programmers to exploit more and try to use other programmable feature on top of it. So after SDN, that was 2015. In 2020, the forum, Open Networking Foundation, they actually coined SDN initially. They came out with a new standard called NGSDN, or a new generation or next generation SDN. The main goal was, when SDN was initially formed, a lot of vendors started producing their own standard of SDN. Right? Cisco, VMware, Citrix, all of them had their own standard of SDN. Now, when that happens, you end up having a common standard. You want to unify their communication, right? And this is where NGSDN comes in. So two new platforms were built. One is called Stratum, which is a operating system that is vendor independent, and a language to program this SDN called P4. Now, there are many capabilities and benefits which are listed here. You can have a look on that. But I want to focus on one term. It's called rapid network innovation. Now, this term, again, looks like a vague term. What it means that, for example, now, if you want to modify a routing protocol, what would be your approach? Would you open the source code of that routing protocol and start changing it? This would be a tedious job, isn't it? Because when you are changing a source code, you don't know what the variables are doing with other variables, right? So what if someone gives you a platform that says you don't have to worry about what's happening in the backend? Use an API and use in a way that, use your own way to modify it. For example, any routing protocol, if you just dissect it, you get only 4 modules inside it. The top and the bottom ones are responsible for interfacing with the transport layer and the MAC layer. Easy. The core 2 modules, one runs the shortest path algorithm. Okay, so in graph theory, you have a whole discussion on SPF algorithm, Dijkstra's and Bellman-Ford and all that. The other one says, how does this particular algorithm will create neighborship with other neighbors or other devices which are connected on the same network. Based on the condition that it makes the neighborship, we have distance vector class and link state class. But your algorithm is fixed. It doesn't see if it is a distance vector routing or a link state routing. It simply sees that, okay, I have got all the information. Now I will find the shortest path out of it. Right? Now, if somebody gives you an API that says you don't have to worry about this neighborship part, right? We'll take care of it. You just put your algorithm on the SPF side, shortest path finding side, and you can just turn an algorithm to a different breed just by putting your code into it with an API. This is the kind of innovation that NGSDN would give. Okay, so creating a new prototype would be very easy, and this will create much more rapid innovation on networking. Now we are moving from software-defined networking to knowledge-defined networking. Now we are gradually moving into an area where AI is, intruding into the area of networking. So KDN, or knowledge-defined networking, was first proposed by Clark in 2003. Reminding 2003 was a year when SDN was not invented. So he had his own view that what if you have a knowledge plane and you have a machine learning algorithm running over a series of controllers, then this would actually behave like a recommendation system. And if you can see this particular diagram, it is a well-known diagram of deep reinforcement learning. You have the perception and the action and the feedback, right? So after that, masters around 2017, when SDN was already developed, he took this idea and made a more, a specific standard, which is called the knowledge-defined networking. Now, this is where the story starts. Now, we have now come across to a point when we know the provisions of using knowledge or machine learning algorithm on top of software-defined networking. So some of the features of SDN, the need of SDN is, first of all, the network control packet exchange is completely diminished, because now routers or switches are not communicating with each other, sending control packets. They are communicating with the controller only. So if I put it a more mathematical term, you are reducing a O of n square problem to a O of 1 problem, because your controller is just one hop away from you, and you only talk to the controller. You don't care about the network diameter, the network topology. Okay, so that's the beauty. The lack of API support, we don't have any API support in the traditional routing or traditional networking, but we have such in SDN. Vendor specific. Mostly, if you are familiar with networking devices like Cisco's or Juniper or HP, they have their own set of protocols, and they don't want to communicate with other devices with the counterparts, right? So SDN is open source. So it is easy to implement, easy to deploy. And finally, it is not hard-coded. I am not going to discuss more on it. If you have question about redistribution, I will talk in the Q&A. Because this particular word will need like 10 minutes for me to explain what is it. Okay, so hard-coded redistribution, which is a feature of traditional routing, is now completely removed in software-defined routing. If I put quickly, redistribution means, what if your routing information is coming from one protocol and going to a different protocol? Because each protocol has their own way of computing metrics. So how do you manage it? The answer is you can't manage in traditional routing. You have to hard code it. You have to go and manually type some values that would do this. Now, if your network characteristics changes, the value remains same. There is no way to automate this process. SDN gives you that process. Some of the differences I also put here for OSPF and EIGRP, two most commonly used routing protocols in the networking. So yeah, if you have questions on the Q&A section on these protocols, I will definitely cover these parts. Now talking about the the enabler technology, MRRF. This term also, which is coined by our lab, most reliable route first. We are inspired by the open shortest path first term. MRRF is a new breed of routing protocols that uses reliability as metric. Now, what does it mean? Think about the traditional routing protocols, right? They uses metrics which are dependent on the link characteristics. Let's say throughput, latency, load, reliability, MTU, hop count. This kind of information were used to calculate the metric, and based on the metric, the shortest path algorithm finds the best path. Now, when we are moving towards this cloudification, cloud computing problems are coming in. A lot of companies are putting the entire network infrastructure into cloud. A new kind of technology was born. It's called network function virtualization. So we are not talking about physical router anymore. What we are doing, we're creating a virtual machine that runs an operating system. Someone's mic is, I think, not muted. Yeah, thank you. Worst case scenario, what may happen? A router becomes very busy and the processing time becomes very high, but the link costs are same. So routing protocol will not detect it, and it will still send the same packets on that suboptimal route. So does the routing protocol doing its job? Yes, but does it do it optimally? The answer is no. Now this is where reliable routing comes in. And in the following slides, I will talk about some of the research outcome that we have got from our lab, and I try to give you kind of an intuition that how can you see this problem solving. Okay, so the first model that we developed, is to create a hybrid architecture where you use a software-defined network on top and create some of the tools in the application plane. And these tools are responsible for replicating your physical topology into a virtual topology and doing all the computation on the server side, right, without informing the devices to exchange any information. By the way, these three layers, application plane, control planes, and infrastructure plane, are the three layers of software-defined networking. Okay, so there's a link of the paper given. If you want to have a look on the inner working, you can go and have a look on this one. Now, extending that feature to SOCDN, what we did, we still have this data plane, control plane, and application plane, like typical SDN, and the data plane is connecting the end devices, like computers or handheld devices, and then the users are using it. On top of this application plane, we have this analytics plane. And this is where all the big data analytics algorithms are being used. Okay, so classification, regression, those kind of algorithms are applied here. Now, there are many applications that you can think of, and our lab is actively doing different applications on it. My area of expertise is to solve a specific type of problem, which is called time series analysis, right? Now, in a very simple term, you can think of that the network is varying its states over the time. So if you can plot it as x-axis as time and y-axis as, let's say, something like load or reliability, whatever, you would get a time series. So is it possible to use a neural network to predict what's going to happen next if I know the history? Well, the theory of neural network says yes, we can. But the problem is, to train a neural network, if it is deep neural network, you need a huge data set. But if you start the network, you don't have data set, right? So you have to build the data set and then use it for learning. And you have to also monitor whether your learning outcome is matching with what is actually happening, which is called accuracy. Okay, so somehow this learning model must self-tune itself, and thus it makes a deep reinforcement learning, not just deep learning, but deep reinforcement learning, because based on the action you take, based on the changes you make on the environment, and based on the feedback you receive from the change, you need to retune yourself. Okay. So now we are reduced into a very specific problem. We're talking about a network which is software defined. So we have a centralized controller that does all the processing, and the data plane devices only forward data. The way they forward data is decided by these controllers, and these controllers are also monitoring how these changes are happening. So they are sending it to the upper layer where these data sets are analyzed, and it is trying to predict what's going to happen next. So if it sees that a node is behaving very fluctuatingly, right? So it fluctuates a lot. So it's not a reliable node. I cannot put that node as a next hop when data comes, because it may so happen I put it as a next hop, I send the data, and the node failed. So this is the usage of machine learning and deep learning model to networking. Now the rest of the slide will only talk about the problem itself. So we developed a tool called Shellmon, which is a monitoring tool that runs on each of the controller. And from there, you get basically a node utilization vector. It's a time series. Of a given window size. And from there, we use recurrent neural network. So the first speaker talked about convolutional neural network, which is normally used for classification. Recurrent neural network is used for regression. Okay. Means given like 3 numbers, what's the 4th number? That's regression. Okay, so this is the function that it is kind of creating, and then it's comparing what's the actual outcome, and based on the difference, it is getting a feedback, and based on the feedback, it retunes itself. Okay, I know this is a very high level diagram, like 10,000 foot view of what is actually happening. So if you have question, obviously I'll be there to answer to get more detailed about this architecture. Okay. Honestly, I'm going to skip this slide because there's too much of maths, and if you have question, I'm going to answer on this one specifically. I don't want to bore you guys. This part is important. So what are the information that we are using for this metric calculation? So we are using something called a hybrid metric. Now, this is never done before, and it was one of the problem that was never solved in computing, that how do you use node cost? I mean, it's not that I'm the one who just came up with this idea that using node cost. This problem was realized far back, and this problem could not be solved because of a specific reason. You see, in state machines or a theory of automata, we know that we can use a finite, self loop. So you can think of that you are traveling from point A. Let's say I'm traveling from London to Kolkata, and I'm hopping somewhere in Dubai, right? Now, if someone asks me how long it will take you to travel from London to Kolkata, I would say, all right, so distance between London to Kolkata via Dubai is this. The average speed of the flight is that. I divide it, I get a time. Yes, mathematically it's true. But is it the exact time I'm going to get? No. Why? Because I'm basically waiting a lot of time in the airports, in the hops. So that time is not computed. It is exactly similar because the routing protocols are only seeing the edge cost, not the node cost. But the problem is, the moment you put a weighted self loop in a graph, this graph doesn't remain a simple graph anymore. And to run a shortest path algorithm, you must have a simple graph. So you must somehow relax those self loop into the edges. This had been a problem for a long time in graph theory, and this is one of my contributions that I solved this problem. The way I solved it is a bit mathematical, I know, but easy way if I try to explain. Think of that time you are spending on the airport. You take that time, you multiply with the average speed of the aircraft, and you virtually add distances, right? Now, when you do so, your network becomes sort of stretched, right? And this time is relaxed on the edges. Now, if you run the same shortest path algorithm, then this algorithm will start avoiding those nodes which are farther than the others. Okay, it's a very vague description of the actual solution, but that's the best I can do at the moment. Okay, so what are the node parameters we are considering? The CPU and memory parameters, number of CPU cores, the frequency of the cores, utilization between 0 and 1. For memory also, the amount of memory we have, the volume of the memory, the frequency of the memory, and utilization of the memory. And for link parameters, we are simply using the 5 golden parameters for link utilization calculation: bandwidth, delay, load, reliability, and MTU. So this is an example. We have a real topology that looks like this. The adjacency matrix would look like that, and this will create a graph that looks like this. Now, this graph is basically being created inside the controller, right? It's algorithmic representation. Now, what happens afterward when you use that technique? So this technique has a name, by the way. It's a mouthful again. It's called stochastic temporal edge normalization. So we call STEN, okay, STEN. The STEN technique will take this graph, and will do some computation, which I'm skipping. This will take the topology as input and do some computation. The reason I'm skipping because there's too much maths involved. So if you have a specific question, I will answer. And this will result something like this. Now, this graph, the one that we got here, is mathematically what we call isomorphic to the actual topology. So these two graphs has exactly same number of nodes, exactly same number of edges, and exactly same number of associated degrees. So any shortest path algorithm that would run on the actual graph, right, would not lose any information if you would have run on the same algorithm on this graph, because these two graphs are isomorphic. Okay, the only change is these distances are changed. So nodes which are busier have put farther from the other nodes. So as you can see here, for example, here node 5 is a very busy node. It takes a lot of time to process a packet. This has put farther than in the graph. So the shortest path algorithm will avoid node 5 when finding a route between two other nodes. And then you get a time series how these values are changing, right? How these values are changing. You get a time series. So you have got like 5 such time series. Each of them has like 144 time samples. And from there, you calculate something called the volatility. We'll come to that point. So before I finish, a quick refresher. Always remember that machine learning is nothing but a fancy way or algorithmic way of solving statistical problems. Okay, the root of the problem was something called curve fitting. We have a curve, the actual function of the curve is f, but the problem is the function is unknown. So the job is to statistically calculate a function called h, or hypothesis, that is the best, the closest function to f. Closer you are, better your algorithm is. Okay, and this error between f and h is what we call the error. Okay, and the optimization function is to minimize that error. An algorithm like gradient descent, it does the exact thing. It basically reduces that error between f and h. Now in statistics, we have something called moments. Okay, to define a data set, we have something called moments. The first moment is the mean and the standard deviation. Then we have kurtosis and skewness in the second one. And finally, we have something called a volatility. Volatility tells you how quickly or how fluctuating your data set is. Now, volatility is a very common term used in finance when stock market predictions are made, which stocks are good, which stocks are bad. These portfolio managements are done. Volatility plays a significant role. Stocks that varies too much is not a reliable stock. So what happens? That, for example, we have this standard deviation and mean, and from there we find something called quality factor. I'll talk about this quality in a moment. And this fuses these two into one graph, and then you use a softmax function. So softmax function takes these ranges and place it into 0 to 1. The reason we do that, because if you don't put it into this 0 to 1 range, because standardization, machine learning algorithms will not give you a good result. Okay. So at the end of the day, we have a reliability graph like this. And then we supply the reliability changes. So the time series of the reliability is fed into the machine learning or deep learning model. And the volatility, which is estimated, uses something called Sharpe ratio. I have a typo here. It should be Sharpe, S-H-A-R-P-E, not shape. Okay, S-H-A-R-P-E, Sharpe ratio. Sharpe ratio gives you the amount of volatility you have in a time series. Now, as I mentioned, the amount of volatility you have is that much unreliability you have. So to find reliability, you simply inverse this value. Okay. So long story short, we have a network that is varying. The node cost is varying. The edge cost is varying. First task, to relax this node cost into the edges. It becomes a simple graph. So now you can use typical shortest path algorithm on top of it. Now, still these nodes these edge costs are changing. So you take a time series of those edge costs, you calculate the mean, standard deviation, and from there you find this Sharpe ratio thing, which is the estimation of the volatility, and then you feed the change of volatility. I'm talking about the second degree term now. Change of volatility into the neural network. So at the end of the day, the neural network will know which node has higher likelihood of dropping reliability in the next timestamp, and that node would simply be ignored in routing. So here the outcome is the controller will try to provide a route which is always most reliable, and here comes the most reliable route first concept. And now if you roll back to the initial problem we had, the ultra reliable low latency communication, so that reliability is now met with this calculation. So yep, some of the experiments that we have done, and these are the experiments results. We found a network of around like 100 of batch size and 512 neurons in the neural network with Adam as an optimizer gave us the best result. Now this may vary on other networks. And just to add on one more thing, these machine learning models are now being evolved, and we have a new topic called federated learning, where different machine learning models are fused together, to create a better machine learning model. Okay, so you can have a look on that one as well. And how to implement it with some physical implementations. We have some physical routers, and I mentioned about the self-configuration. So you can now write a simple Python script that can inject code into this router, and the injection will carry data which is coming from this optimization function. And then to enhance it a bit more, you can use threading, because Python is a programming language, it supports threading. And if you put threads, what happens? He's the first one that uses no threads, and for 3 routers we took 20 seconds to configure, because it was happening one by one. If we do threading, it brings down the time to 7 seconds, is 1/3 of it actually. Okay, so with the help of the programming languages, you can make this automation even more tuned or optimized. So yep, some of the example that you have a typical network topology, and from there you create a graph. From the graph you use the optimization, you find all possible paths, and the best path is fed back to the network. And this completes the whole loop. The closed loop problem is made, and this is a benchmarking of deep reinforcement learning. Before I finish, I'd like to acknowledge my laboratory, Suit Lab, Smart Intelligent Internet Technology Lab from LSBU, the funder of my project, Horizon 2020, the Defense and Security Accelerator Program from the Defense Ministry, UK, and the Innovate UK Cyber Accelerator Program for funding my research for last 3 or 4 years. So here, that's my time. I'd be highly appreciate if you have questions. And I will try my best to answer. Thank you very much.
One second, Professor Ghosh. Actually, there is a problem in our streaming. Just last 3 seconds, we had a problem in that YouTube streaming. Just okay. Bear with us. I will get back to you.
Sure, no problem.
May I please request Shobhik to carry on?
Okay, ma'am. Thank you so much, sir, for your guidance in cognitive routing for beyond 5G networks. Now I invite Professor Rishi Bhattacharya for the QA session of this lecture. Sir.
Thank you, Shobhik, and thank you, Professor Ghosh, for your wonderful lecture. Coming directly to the question answer part, Mukesh Kumar has a question for you. He's asking for the disadvantages of 5G. The disadvantages of 5G, you have to explain. What are the disadvantages of 5G? And is there any disadvantage or something like that?
Okay, I think, I mean, as he's not specific on the question, I think he's referring to the new, the legal issue going on with the 5G problem, right? That 5G is killing birds. Just to counter that, it's not because I'm doing research in 5G, so I have to defend it, but let's give you some more quantitative data. Human tissue can tolerate up to 5,000 millimeter of radiation. Okay, so radiation with 5,000 millimeter of wavelength, human tissue can tolerate. 5G with this new millimeter wave communication with 300 gigahertz, which is the maximum frequency that is being offered by 5G companies, is just 1 to 10 millimeters. So yes, any radiation is bad. Even when you are in sunlight, you are still exposed to radiation, but it is not something that biologically harmful to your tissue. Secondly, if you see something called SAR value, you can find on your phone, and these are the numbers which are calculated after experiments on living being, and by checking that whether this particular radiation threshold is exceeding the human capacity. If it is not, then only governments support it or approve it. Now, disadvantage, I think of one of the disadvantage is, yes, there would be more radiation. There will be more radiation because in typical 4G network, we see mainly two types of antenna. One are the frontals, I mean the one that you connect with your phone, and the microwave antenna, the backhauls that connects the antennas themselves, right? In case of 5G, you have a new technology called HETNet, or heterogeneous networking, or small cells, sometimes called small cells, where you are putting a lot of antennas, you are deploying a lot of antennas, and they are not placed in that height, they are closer to the ground. So basically what would happen, you will be exposed to more interference. Yep. So from the human's perspective, that is not good. Sorry, that is not harmful. But from the perspective of other animals, I think there are some implications, because I think I read in some paper that with that much of radiation, that much of interference, birds that stop navigating themselves. Okay, so this is, I think, one of the example that I can think of, but it's not as deadly or catastrophical that sometimes surfaced. So that's my answer to this question.
Thank you, sir. Thank you, sir. Thank you for your answer. Back to Shobhik.
So we have almost come to the end of today's session. Now, I would like to call upon Professor Moinuddin Sheikh, Joint Coordinator of BVOC Studies, to sum up the entire webinar proceeding of the 2 days. Sir, please join me.
Am I audible?
Sir, yes, sir, you're audible.
Okay, thank you. Thank you, Professor Shobhik. We are at the last moment of our 2 days international webinar on artificial intelligence and data science. I will give you a quick summary of our current webinar. This webinar dedicated to our memory of our Dr. Pooja Chatterjee and Dr. Nandan Ghosh, as we lost 2 of our young colleagues in this pandemic. This webinar introduced about a popular and current topic in the domain of computer science. On yesterday, Dr. Paramartha Datta has presented us in a very beautiful way about machine learning. On the other hand, Dr. Sunil Karfarma has explained about the security issues on big data with his nice presentation. Not only that, he also explained about the concept of cryptography and steganography with the help of Hadoop architecture. Dr. Sripati Mukhopadhyay explained about the association rule in data mining with a very beautiful example and in a very simple way in front of our participants. Dr. Amlan Chakrabarti gave the first of all the lectures we have heard today. His lecture covered deep network techniques for computer vision. He explained the history of deep learning as well as how convolution neural network works. That was very interesting. He also explained the relation between convolution neural network and traditional neural network. A wonderful lecture session provided by Dr. Parish Chakrabarti. He explained that what are the criteria to implementing a successful artificial intelligence system in an organization in details. At the end of our lecture session, Professor Shropto Shikosh explained the application of artificial intelligence in data routing with the help of cognitive routing algorithm. He also explained the pitfalls of old routing algorithms beautifully. I hope this webinar will help all kinds of our participants like students, researchers, and faculties. Artificial intelligence is a vast area. Machine learning, deep learning, data mining, security issues on big data, all are related with each other under the artificial intelligence. Study of artificial intelligence and machine learning has a bright future scope in the near future. Demands of artificial intelligence increases exponentially. Some top career options for machine learning and artificial intelligence include data scientist, AI engineer, big data engineer, robotics scientist, and many more. We have received a good number of responses from participants of different areas. I have been seeing a lot of comments in YouTube that the queries regarding artificial intelligence are endless. We could not answer everyone's questions due to lack of time. Although we hope we have been able to satisfy everyone's curiosity about artificial intelligence and data science. Thank you all for being here and taking the time to patiently listen. Again, I thanks to all our speakers for their valuable speech. Thank you. Over to Vincent.
Thank you, sir. Before I sign off, I request Dr. Bidisha Sen, Coordinator of BWOC Studies, to propose the formal vote of thanks and end this seminar. Thank you, ma'am.
Thank you so much. Am I audible?
Audible. Yes, ma'am, you're audible.
Thank you so much, everyone. Though it's a very formal kind of a thing to give vote of thanks, but I really, truly want to thank everyone associated with this webinar from core of my heart. Primarily, I want to thank our Vice Principal, Sir, Professor Apurva Roy, our BART Sir, Dr. Manush Kobe, our IQAC Coordinator, Dr. Tathagata Rai Chaudhary, and prominently our Chief Advisor and Examination in Charge, Dr. Chandramuli Sengupta, for their true inspiration. I want to thank the entire BWOC department for their tireless, their enthusiasm, for their initiative to do this webinar and to make it so very successful. I want to specially mention the name of Professor Shantanu Modok and Professor Rishi Bhattacharya for their so very true initiative. They wanted to make this webinar so very special and so very successful. I want to thank all of them. I want to thank Dr. Moon Jana and Professor Sritama Chaudhary from Social Media Cell for their logistic support. I also want to thank Mr. Oshijit Roy for the beautiful YouTube streaming. And nonetheless, I want to thank all our valuable participants for their presence and how the way they made this webinar so very special and so very successful. We have just completed a successful webinar. I really do hope we will see you all to another great webinar that is on our next planning. Thank you all. Have a great day ahead. And with that, I want to conclude this webinar. Thank you so very much all.